Welcome back, wizards. In case you're wondering, yes, it's been a while since my last video. I am still working on assignment 2, um, but I've had some things come up. So normally you would have 4 people working on this this assignment, but I'm just one man, and I also have a full-time job, so I just don't get as much time as I want to on it. But yeah, I've had some other things come up, like I actually recently ordered in this book, A Tour of C++ by Biane. Couldn't put it down, so I've sort of been focusing on this as opposed to the assignment, but that's all right. What are you going to do? I'm just doing this for fun anyway. And also, I got another book. This is actually free online. You don't have to buy this in paperback. You can buy it so you can just get it as a PDF for free. Performance analysis and tuning on modern CPUs. This was so interesting. Another book that I just can't put down. So my knowledge of computer hardware and computer architecture, I guess, is not probably not up to scratch yet to fully read this book properly, but still, it's really interesting how performance analysis is done, um, mainly using C++. Yeah, it's really cool. So if you're interested in that sort of thing, check it out. Just Google it. You can find it for free. But anyway, so with the assignment, here's a bit of an update. It's not finished yet. Basically, I've gotten to the point where all I need to do now is create the abstract syntax tree. So the parser is essentially mostly done. The grammar itself is pretty much done. There's a few things that aren't finished that I want to improve on. Um, the grammar ended up being heaps longer than I thought it would be, and I can only imagine how long grammars are for more complicated languages like C++ and yeah, there's probably way more complicated languages and grammars out there. So basically, I used Bison to do this. Bison requires 2 input files. It requires your Lexa input file, this one here. I had to rewrite my existing Flex input file, which is what I did for assignment 1, to instead of returning all of the more generic things like symbols and keywords, I had to return each individual symbol and each individual keyword. So when you inside the Flex rules, when you return these keywords, I guess you call them. I'm not 100% sure. These are tokens. So you return these tokens specifically to the parser file, which is this here, the .y file. Bison reads this and gets. I'm pretty sure it uses Yak to create the parser at that point. So we start off by importing the tokens, defining some types. For example, all of these divide equals etc. is a symbol. All of these tokens are keywords, and we can use that later to build our abstract syntax tree. Then you define the actual grammar. So the grammar starts off with a program which can contain statements. Statements can contain a single statement, or it can contain a single statement concatenated with more statements. This grammar ignores white space. It ignores new lines. So it can parse the Ada programming language as it was intended without worrying about white space and new lines. I had some challenges building this grammar. First of all, I had no idea where to start, so I just I looked around and I saw how other people had done not the exact Ada language, but like similar grammars, and I took things from that. Obviously, starting off with the program at the higher level, statement, expressions, you know, return statements, function call statements, etc., etc. Another problem that I had was I had a bunch of okay. So initially, I started out. I thought I understood everything. I thought I had nailed it. So I started smashing out this grammar. Just wrote this massive grammar. Didn't test it or anything. Didn't develop it iteratively. And then when I actually ran it, I had all of these shift reduce errors and shift reduce conflicts and shift and reduce conflicts. And I had to selectively remove productions in order to narrow down exactly where the errors were coming from, because I had like 800 errors or something like that, 800 conflicts. So that wasn't good. But I picked up a few things to help me develop the grammar without getting shift reduce conflicts and reduce conflicts. One example of that is here, the return statement. So the way I figured this would work is in Ada language, a return statement can either be an empty return statement. An empty return statement is simply the word return. That's it. That's totally legal Ada language. It can also be a singular return statement where we return a single value. So what we do here is we use the empty return statement inside our definition for singular return statement, and then after that it'll be a primary expression. In this case, primary expression can just mean basically any value that we can return, like a string literal. Well, I can actually show you exactly what it is. Primary expression can be an ID, string literal, integer literal, character literal, true or false. It can be a function call statement, because if you can return a function, right? You can return a function call expression. So you could, for example, you could return f of x. That's totally legal. You could also return, obviously, negative integers. You can return some value from an array. So if we have my array at index 5, you could return that. That's totally legal. You could return some negated version of all of these. So you could return, I don't know, not x. Yeah. Then back up here. Then the return statement could also be a list return statement. So we could return a list of primary expressions. So we use the previous definition that we had of singular return statement, and then the terminal comma, and then finally a primary expression list, and that would look like this. Return some singular return statement. So this, I'm just going to put brackets around this. This is a singular return statement, and then a primary expression list would look like, comma. Primary expression list could look like, again, anything. We could return f of x. We could return some literal. Yeah. So what this does is, using the previous definition, it's allows you to build out these potentially large potentially large productions with many different branches without causing shift reduce conflicts and reduce conflicts. So yeah, that was pretty fun to learn. I found it pretty challenging, which is good because that's what I'm doing this for. I'm trying to learn. Yeah, that's pretty much it. If you want to have a look at it, you can go through, look up this GitHub link here. I'll leave a link in the description. But yeah, this is not complete. It doesn't parse everything yet. I still need to figure out a few kinks. And it also does not generate a abstract syntax tree yet, which I will be doing. You can see here, after a production has been parsed, or after a non-terminal has been parsed, you can then input C code as a rule to do something after that. And what I need to do here is literally create a data structure that's going to contain my abstract syntax tree, which we'll then use in the next step to do semantic analysis. Was there anything else? I think that's pretty much it. I am going to continue going through the lecture notes probably before I finish this, because I want to get through them. I want to learn more. But this assignment is taking up a lot of time, so I don't want to spend months on this getting it perfect and missing out on, the time where I could have just been learning more about compilers. So I'm gonna do that. Hopefully I'll finish this soon, but who knows? Anyway, thanks for watching. See you in the next video.